All right, it looks like we're getting it to record, so that's good. Okay, so over joint on your finger, tip of the nose to the tip of your finger was a yard on the king's in the king's domain, and we were dealing with how do we get those rules of thumb for estimation. Couple of housekeeping items. I will not be here on Friday. There will not be a class on Friday. There will be a quiz, however, and I think it will show up on Thursday, and you have all weekend to do it. I did send out an email to anybody who had not logged into WebAssign yet, because remember that most of your grade is based on homework, and you do get a bonus for doing your homework early. But there are a bunch of you who have yet to log into WebAssign, which means you're already losing points because the first assignment was already due, even though it was a getting started assignment. That's 10 points that were super easy to get. So just be aware of that. So you want to make sure you're in WebAssign, getting those things going. You do have a quiz on Friday, and we won't be meeting class on Friday. So because I'm out of town, but the quiz will cover us. So, this is where I left you on Friday, was there's a statement, that this is a meme that goes around in Facebook that says there are more atoms in a teaspoon of water than there are teaspoons in the Atlantic Ocean. So the question is it true? Does anybody know whether it's absolutely true or not?
Yes, depends on literally.
Have I lost Enid? Are the Enid folks there?
It's true.
Okay.
Can you not hear us?
Yeah, I hear you now. It's just that I've got a screen on top of you guys, so I don't necessarily see you moving. That's why I was double checking.
Gotcha.
So the answer is, yeah, it's true. The question is by how much, okay? The question is by how much. So, so what kinds of information are we going to need to know in order to do this?
How many teaspoons? Milliliters
so
in a teaspoon.
We need to know how many teaspoons are in the Atlantic Ocean. So where are we going to find that information? Google. You can get Google, but is Google going to give you teaspoons? You get a volume. Google will give us a volume. I can go out and get a volume. So I did go out and get a volume. So we'll slip the statement up here. I did go get a volume. According to NOAA, the National Oceanic Atmospheric Administration, good old NOAA, it tells me that now this is the fun part, because the Atlantic Ocean has arbitrary boundaries, because the Atlantic Ocean is connected to the Antarctic Ocean, it's connected to the Arctic Ocean. So it's kind of got some interesting boundaries, but given that the NOAA gives the accepted volume of the Atlantic Ocean at this right here. In kilometers cubed. So it's roughly 310 million kilometers cubed is the volume of the Atlantic Ocean. Well, I got to get that to teaspoons. So I'm going to have to get some conversion factors there. So does anybody know? So one of the conversion factors that I'm going to use is I'm going to do 5 milliliters is essentially 1 teaspoon.
Yeah, that's what I was going to say.
And that is a common conversion. So 5 milliliters is 1 teaspoon. That's going to help me out in a couple of different ways, because I got to know teaspoons for the number of atoms, and I got to know teaspoons for the Atlantic Ocean. So converting this, I want to convert that into milliliters to get that. So I'm going to start out with 3.104 times 10 to the 8th kilometers cubed. If I do my conversions into centimeters cubed, and why would I want to do my conversion into a centimeter cubed?
Because 1 milliliter is 1 centimeter.
1 milliliter is 1 cubic centimeter. So when I do that, I end up with 3.104 times 10 to the 23rd centimeters cubed, or milliliters. 3.104 times 10 to the 23rd centimeters cubed is milliliters. Then I got to divide that by 5 to get teaspoons, right? So I divide that by 5 to get teaspoons, and I'm going to get 6.208 times 10 to the 22nd teaspoons. So that's how many teaspoons are in the Atlantic Ocean. So I got that part. So I got to know number of atoms. So what other information do I need to know?
Density of water.
Well, I got the volume in teaspoons. I got 5 milliliters is 1 teaspoon, so I got that part already.
Dr. Whitblack, would you mind moving your paper up a bit?
Sure. That help?
Thank you. Yes, ma'am.
Okay. So I need number of atoms.
Moles.
How many moles in a teaspoon?
Well, it'd be
I'm
a
going to
mole.
need the number of
You'd have to
moles,
use-
that's for sure. I need the number of moles. So that's 6.02 times 10 to the 23rd, and that's my moles. Or that's number of atoms per mole, right? That's number of atoms per mole. So I'm going to make an assumption. First of all, I'm going to make an assumption that my teaspoon is totally water. All right? Is it going to be totally water? No, but its majority of it is going to be water, right? So majority of it's going to be water. So that's the chemical formula of water is H2O, right? So I've got 3 atoms per molecule. I got 3 atoms per molecule. I've got 18 grams per mole for water. So I've got 18 grams per mole for water. So if and we know the density of water, if I'm assuming fresh water, and that's what I'm going to assume for this estimation problem, I'm going to assume fresh water. I know that 1 milliliter is equal to 1 gram of water. Okay, 1 milliliter is equal to 1 gram of water because my density of water. So there's 5 grams of water per teaspoon. So I get 5 grams of water per teaspoon. There's 18 grams per mole. And so if I do my 18 grams per mole and my 5 grams of water, it's 0.28 moles H2O per teaspoon. So I get 0.28 moles per teaspoon. And then I can get, then I use my good old Avogadro's number. So now I get 1.67 times 10 to the 23rd molecules per teaspoon. And then I have to multiply by 3 to get 3 atoms and I get the number is 5.02 times 10 to the 23rd atoms. So I get 5.02 times 10 to the 23rd atoms compared to what's up there at the top. If I scroll this down just a bit, times 6.02 or 6.2 times 10 to the 22nd, 5.02 times 10 to the 23rd. There's an order of magnitude more atoms in a teaspoon than there is than there are teaspoons in the Atlantic Ocean. So when you're doing estimations, and part of the reason I do this problem is a couple of things. One is we're doing some strange conversions, right? We're taking teaspoons and cubic kilometers, so we do some strange conversion factors. We also see the order of magnitude in numbers, so that's one of the reasons I do this problem. And we get a feel for, I've got to go get some information in certain cases. And as engineers, a lot of times you are going to have to go and figure out where am I going to get this information, or how am I going to get this information, or what equivalent could I use? One of the assumptions we used was we're going to use 100% pure water in our teaspoon. We know that's not the case, but that's what we're going to use for that assumption. By doing that assumption, first of all, when we're dealing with numbers on 10 to the 23rd, most of the time, even with salt water, the majority of that teaspoon was going to be straight water molecules. So that's our pretty good estimation that I'm going to be able to use. So we have to be able to make some assumptions. And then one of the other assumptions that we had to make in this particular one was our boundary conditions, because none of us really know where the Atlantic Ocean starts and stops. And that doesn't necessarily count, does the Gulf of Mexico part of that Atlantic Ocean or not? You know, it's an arbitrary dot on or an arbitrary line on the map. We just happen to use what NOAA used as an established figure for the estimate. So that gets us some information that we need to have as we start dealing with some of the estimations. So chapter 1, what you've got in your chapter 1, now I don't necessarily care whether or not you have the hard copy book or not. I will tell you that I don't necessarily care whether or not you drag your physics text to class. But I will tell you that the examples are very, very useful. We will go through some of those examples. I will tell you that the back of each chapter is extremely useful because it gives you the summaries. So those are very critical pieces. Another thing that I will also tell you is when you get into WebAssign and you're dealing with WebAssign, and because of our internet systems, both here on Enid and here in Tonkawa, evenings cruddy to get on the internet to get stuff. This is what I would recommend you do, since I know several of you are doing sports, several of you are doing a bunch of things. When you first go into WebAssign, print out your assignment. Print it out. Get it on a printer and print it out. You will also have, in each of the boxes, when you print it out, there'll be a box with the problem kind of outlined in it. And you'll get something like CP, I think ours is EP, or there's a number there, and it'll have a number after that. That's that first set of numbers that you'll see on those problems, that's the book designation. That's the book that you've got, okay? That happens to be the College Physics Text Edition 10. That's what the CP is. I think yours is EP and then whatever the edition is. Then there'll be 3 numbers. It'll be like 001. That will tell you what chapter the problem came from. So if you're going to your textbook, that's going to tell you what chapter it is. Then it will tell you P, and then you might get an EX, or you might get a TA, or you might get some other letter designation. That's WebAssign's designation for whether it's a tutorial, whether there's help associated with it, whether there's a video associated with it. So that piece doesn't really help you out a whole lot, but this next part does. So it gives you like 0012. That is, if you go to the back of your chapter, that tells you what the problem is in the back of your chapter. So this designation would be the end of chapter problem 12 for chapter 1. The reason I tell you that is because several of your book problems, if you go to the back of the book, has the answer. What WebAssign is going to do is, if the text says that this is at 10 meters per second, your WebAssign may say that this is 13 meters per second, so this is the text value. That's the WebAssign value. Well, if I can work the problem using the text value and solve it, then I've already figured out the answer, and now I can just go in and plug and change the variable. So that gives you a way to, without using a chance up in WebAssign, it gives you a way to validate some of your answers.
So the 001 is chapter 1,
Mm-hmm.
and then the 1, 2.
It's the end of chapter problem number. So if I were to assign you homework, go to do the end of chapter problem 12. That's how that would be designated in WebAssign. That you can go back and actually read the way the book does it. Have how the book has it. The reason is that way you've got another opportunity or another chance or a practice problem that you can go to be able to look at it. The other reason I tell you to write, or go ahead and print it out, because those of you, how many baseball players do I have in here? I got a bunch of you, right? I got a bunch of you. So when you're on the frickin' bus going to the baseball game and you're trying to work your problems, you don't have internet, do you? Not usually, but you can work it out on a piece of paper. Okay, you can work it out on a piece of paper. You have the piece of paper, you can work it out. And I will also tell you that sometimes, like I said, WebAssign gets kind of persnickety. So if you've got something that's like X of O and it's not accepting it, if you have it worked out and come by my office, I see that you have it worked out. Okay, you can, and sometimes the internet will be down and you can at least show me that, hey, I got the paper copy, you know. So that, and you can take a picture of that paper copy and send it to me. And I can actually go in and look in WebAssign and see where stuff is. So if there's a problem with WebAssign or there's a problem with WebAssign, you know, as we get into a couple of them, I still keep the problems even though I know that there's a couple of issues with them, that at least I can compare what you guys have worked on and be able to see what's happening. But you want to kind of look at that. So that's a trick to help you with WebAssign and help you go back and forth. And when you go to the end of the end of chapter problems, or the summary right before the end of chapter, that's really handy and useful for being able to see where all your formulas are. It's kind of like a good cheat sheet to have. And then we have, I like Searway better than some others because it's a nice way to deal with those examples. He does a lot more examples that are out there. All right, one other fun thing. Let's do a real quick trick review. So when you guys are dealing with, we're going to use this lovely triangle a lot. As I teach engineering physics, I will show you where the calculus comes in. But a lot of the engineering physics concepts and a lot of the concepts are all based off a trig. So I'll show you where, and in fact, we'll get to some of that today. I'll show you where the calculus comes in, because one of the reasons that we have calculus is it was in order to explain a lot of the physical phenomena that was going on. And when we get to talking about Newton's laws, which I'll show you Newton's notebooks, and we start talking about where some of the calculus comes in. But we're going to take this lovely triangle. And this is how I do it. I don't use X and Y. I typically will write my triangle out like this, and I will show you why. So here's my angle. So there's my angle that I've got. Those are my three sides of my right triangle, and this is a lovely right triangle. So there's my lovely right triangle. I'm going to write it out like this. This is the hypotenuse. This is the opposite. And this is the adjacent. So I've got my triangle, the hypotenuse, opposite, and adjacent. So if I were to use X and Y, the adjacent would be X and Y would be the opposite. However, when I'm working my problem, I might be in that configuration. I might know that angle up there, and my adjacent would be Y, and my opposite would be X, if I were in my Cartesian coordinate system. So if I do it this way, if I do it with opposite and adjacent and hypotenuse, I can move that triangle around and make that triangle like that, and I don't care. I don't care what's X or Y. So it's just easier for me to be able to move that triangle around so that I don't have the X or the Y, and I don't have the opposite or the hypotenuse. You know, I don't have to keep track of all that crud. So I keep it that way. All right. But that means, if in this configuration, that the sine of the angle is going to be the opposite of the hypotenuse. The cosine of the angle is going to be the adjacent over the hypotenuse. And the tangent of the angle is going to be the opposite over the adjacent. And now I don't get confused with my Cartesian coordinates as x, y, or whatever, right? I don't get confused anymore, and I can move that triangle around the way I want to. If you want a real good trig refresher, the appendix in our book really is a nice refresher. You might look at a couple of the trig identities, things like the cosine squared of the angle plus the sine squared of the angle is equal to 1. We will use a lot of those identities. We don't necessarily use law cosines in here, but when we get to statics, you'll use law cosines. So that's most of your trig that you're going to use most of the semester here. The other part is the hypotenuse. Good old Pythagorean's theorem. A squared plus b squared is equal to c squared. So you've got that information in there. So there's your trig review. Okay, that's your trig review, and that will help. And so for those of you who were in lab last week and you did your trigonometry in order to measure the height of the building, there's your solution, right? In fact, we're going to do one of those. I've got a surveyor measures the distance across a straight river using a tree on the opposite bank. And we've got, using a tree as a reference on the opposite bank, walks 150 meters, and he sights the tree at a 32-degree angle. Question is, how far across the river is it? Now, our book gives us a methodology to work the problem. And I don't care how you guys do it. It's another reason why I point you to the back of the book, or I point you to being able to print out your problem. Because some of you, it makes more sense to do this. Well, here's a piece of information that I know. I know that I've got 150 meters. I know that I've got a 32-degree angle. And what I'm trying to find out is, how wide is the river? So some of you may want to underline it and work through it. First thing you want to do is, like I said, you read the problem. Then you draw the diagram. So I've got a riverbank here. I've got a tree. Okay, there's my tree. This is the variable we want to find, how wide across it is. He's told me, and the problem tells me that I've walked 150 meters there. And then I'm going to sight in my tree. And that is a 32-degree angle. If this is a test in my class, and you had this problem on the test, by drawing the picture, you've got at least a point. You leave it blank, you get 0. Right? You draw the picture, you get at least a point. And those of who have had me before, or you've heard before, sometimes the more creative the picture, you might even get some creativity points. So if you're totally stumped, draw the picture. I mean, you can't hurt anything. Draw the picture. The next thing is, this one we sort of told you it's a basic trigonometry problem, right? So it's a basic trigonometry problem. So I can either use sine or cosine, right? I'm going to want this one right here. So I'm probably going to use tangent. So now if I say, all right, the tangent of the angle is equal to the opposite over the adjacent. And I've written the equation that I need. So now I've got my toolbox. I've written the equation that I need. Now you got at least 2 points. Because I'm going to give you credit if you write down the right equation. All right? Or an equation that will work. It doesn't necessarily have to be the equation I'm expecting, but the equation that'll work. So now, this is something that I'll tell you, it drives me crazy. And there are pros and cons to this next step that the book tells us to do. So now I'm going to rearrange my equation to solve for the unknown that I want to solve for. So there's my adjacent, there's my tangent, and that equals the opposite. All right? So I rearranged the variables. Okay. I don't always say it's to wait to this point to add in your numbers. Sometimes it's going to make more sense to add in your numbers earlier than later. The book, the way our authors do it, they have you solve for the unknown first and then plug in all your variables. But you guys know that sometimes carrying all your unknowns when you can group numbers together might make more sense. I don't really have a preference which way you do it, okay? You could have plugged in my numbers up there and done it whichever way you want to do it, but by doing it, at some point you have to plug in the numbers, and at some place you have to solve for the variable that you're after. It's up to you. In some problems, it'll make more sense to do it one way or the other. This is also a good time to do your unit analysis to make sure that your units make sense. So in this case, we're going to have, this is in meters, and that's in meters. The tangent is a ratio, so my unit analysis balances out. All right, my unit analysis balances out. I have meters on both sides, so I know I've done my arithmetic correctly. I know I've done my adds and my multiplications and my divides correctly. So that's all good. And now I'll put my 150 meters in, the tangent of 32 degrees. And if my calculator is set up correctly, I can plug in the numbers. And when I plug in the numbers, I didn't plug it. I don't have the answer on my page. Anybody got a calculator out handy? 93.7? 93.7 meters. Yes. That's also something, guys. Let me show you something. I use the Latin 7. So you'll see it in my notes and you'll see it around. I use the Latin 7. And the reason I use the Latin 7 is makes it an easier variable to see, because some of you will write a 7 that looks like that. Is that a 7 or a question mark? Or is it a 1 that your pen just got sloppy? I use the Latin 7 to help make it clearer. Okay, that's just something that I lived in Panama for 4 years, and it's a habit I got into. I also a lot of times will use the Latin Z with the line through it as well, to make sure that it's just not a squiggle or a 2 or something out there. So that's just my writing style, so that you guys, when you're going through the notes and things like that, you'll be able to tell what that is, and that's the reason behind it. It's because as we get to writing fast, things get a little sloppy, and it helps to distinguish whether that's a 1 or a Z or a 2 or something along those lines. So that's just a habit that I have, and it does help. So when you look at those notes and going back and forth. So now, hopefully, you know how to solve your height of your building problem, right? Yeah. Okay. Now, one of you guys' homework problems does not have a 90-degree angle in it. One of the homework problems does not have a 90-degree angle in it. Yeah, nice. And in your drawing, your picture will show you that it's not a 90-degree angle. Okay. Now, but you can always, and remember, when I deal with triangles, that's one of the beauties of trig. Okay, one of the beauties of trig is, even if my triangle is like this, okay, that doesn't have a 90-degree angle in it, right? But my trig identities will tell me if I do this, I can get 90-degree angles. And by doing that, one of these angles, like I think it's this angle and this angle are the same, because I can use a law of a right triangle to get my angles the same. So by using a triangle, in any case, the stretch of the imagination, I can usually come up with a right triangle. Yeah. Now the wording of this particular problem was, a surveyor measures the distance across a straight river. Okay, so I'm told you it's a straight river. And I'm using a tree on the opposite bank as my reference point. So I actually set this one up to be a right triangle. Okay. And the wording is kind of going to tell me that that's going to be the case. Now, I can do this kind of a triangle, and then I can go use my law of cosines as well. Most of the time, we're just going to stick with, because we're trying to learn concepts, I don't necessarily get that persnickety. But there's one of the problems, I think, in the homework, and I like it because it's a really nice way of you have to draw the problem correctly. I'm standing at a stop sign, or I'm standing at a sign, right? And there is an object here, and there's an object here. And I'm going to have, and I know this distance and I know that distance, but I'm wanting to find the distance between the two.
Okay.
Well, that's not a right triangle. And so this one is more about going ahead and using your trigonometry to get there, but I can set this problem up and I can build right triangles all over the place. You know, so it's more the logic of how to find that distance than it is just going straight to log cosines. And that'll come up in the chapter 2 homework, is where that one's going to come in. So that problem.
Hey, Dr. Wilbeck, I got a quick question for you. Do you have like the rule where if we have a word question, we have to answer it with a complete sentence, or are you okay with just like a number?
Because I'm using WebAssign, it's going to be a number.
Oh,
If on the exams, I will tell you that there'll be like some exams you'll have step-by-step problems. I need you to tell me clearly which variable it is or which number it is or what it is. And I'll give you a for instance, because we just did this today in statics. I had a problem in statics, so there's my horizontal, and here's my vertical. And we are given that angle, okay? And I had two forces. Okay, so I have my two forces, and so we were going to do the resulting force. So the resulting forces, I've got a vector, I can add them head to tail. And then I had to get my resultant. So here's my resultant. This one just happens to work it out. But the angle I calculated was this. The angle that the book wanted was like this one. So you're going to have to clearly show me on a graph which angle it is that you've solved for. Because you could give me this and that'd be totally correct. But if I've asked for this, I need you to take the next step. Or vice versa, okay? Now sometimes I'll just say, give me the direction and magnitude of that vector. Well, if you give me the direction and magnitude of that vector, I don't necessarily care what angle you give me, just clearly show it on your diagram. So I'm more concerned about the diagrams than I am writing out the answer that says the distance across the river is X number of meters. That wastes time on an exam. And I'm not too worried about it. Now, if I'm asking you to explain this concept, okay, I'm asking you to explain that concept, then I want you in complete sentences, okay? But that's a word answer to a word problem, not a numeric value to a word problem. That answer your question?
Yes, ma'am.
All right. Okay. So now let's start jumping into stuff. Oh, God, I got to do one more thing. Good gracious. All right, I'm going to get there. Talk about one more piece of the puzzle here. We're going to use a couple of different coordinate systems. This is our typical Cartesian coordinate system, so that's X and Y. And I probably have Z coming out of the page. Okay, so that's my typical coordinate system. Good old Cartesian. So now if I'm doing a representation of this vector, so there's my vector. I can represent that vector in 2 dimensions. I'm not going to worry about Z. That particular point will give me my normal Cartesian points, X and Y. All right? The other common system we're going to use, right? The other common system we're going to use, which gets us into our right triangles, there's my angle, and the magnitude of that vector is the letter R. I can do it in polar coordinates. And my polar coordinates, that same position can be written out as R and theta. So I can do it in either Cartesian coordinates or polar coordinates. And as we start getting to circular motion down the road, we'll be dealing a lot more with the polar coordinates. So you're going to kind of want to know how to go back and forth between my polar coordinates and my Cartesian coordinates. So if I do that, I'll get my other color. Did I bring another color in? Yes, I did. I brought another color in. So there's my X and there's my Y, and I've got my right triangle, and I can use that Cartesian coordinate system. So I can keep those things going back and forth. Okay, I am going to get started with a couple of things before we abandon today. So now let's see if I can switch to the computer without getting totally haywire. All right. Maybe. Okay. All right. So when we talked about derived and fundamental units on Friday. We said my fundamental units were length, a unit of length, like X, my unit of length, my unit of time, seconds, my unit of mass, kilograms. If I'm using the SI system, I'm in kilograms, meters, and seconds. If I'm using the CGS system, I'm in centimeters, grams, and seconds. If I'm using the English system, I'm in slugs, feet, seconds. So I have that. So when we're dealing in physics, particularly in this first part of physics, we're going to talk about how things are affected. And we're studying matter, that's stuff. And we're going to talk about how Newton actually looked at matter as being different than weight. Weight is a force. Weight is a derived unit. And weight's going to be in newtons, or weight's going to be in pounds. Weight's a force. So I'm going to have that derived unit. So we're going to have matter. We're going to deal with energy. We're going to deal with motion, and we're going to deal with force. So those are the things that we're going to start dealing with this semester. Now, one of the things that we're going to start with is we're going to talk about kinematics. That's where we're starting. It's motion. That's where we're going to deal with motion, and we're going to get into velocity, acceleration, and we're going to start with the kinematic equations, and we're going to get there. So we're going to start in one dimension. We're going to be really precise about our words for like the next week, and then we're going to get sloppy about our words again. Okay? We're going to be precise to get started, and we're going to get sloppy after a bit. So one of the things that we're dealing with when we're dealing with motion is we have to know where we start, and we have to know where we end up. And that distance between the starting and the stopping point is going to be called displacement. And I can have that a positive displacement, or I can have a negative displacement. It's going to be relative to whatever my reference point is. So when I'm talking about I've moved to the right 3 feet, that would be a positive displacement. Or if I say back up 3 feet, that might be a negative displacement. So my displacement is going to be a little bit different. So motion, we're going to talk about displacement, we're going to talk about velocity, and we're going to talk about acceleration. And we're going to use some different language, just a little bit of different language.
On displacement, if you go forward 3 meters and then back, is that 6 or is that 0?
That one would be 0 because the question is, where did I start and where did I finish? Right. From the reference point, exactly. So when we talk about displacement, we're talking about where I start and where I finish. And so if I move forward 3 feet and I move back 3 feet, what's my displacement? My displacement's 0. What's the total distance I traveled? 6. It's 2 different questions, 2 different ways of looking at it. And I will warn you, as I go through the semester, that I may have my notes as one way and then I ask the question in class a different way. And because I asked the question in class a different way, the answer's going to be different than what's in my notes. It's very much like that question right there. The question being, what was my displacement versus my total distance traveled? Right? So for here, if I'm traveling from this spot right here to Tulsa, right, I can have a displacement and I can have the distance traveled because there's how many ways to get to Tulsa? Bunch of different ways to get to Tulsa. So my big thing is, what's my frame of reference? Which is why you got to draw your picture, okay? What's my frame of reference and where we're going to be? And that's where I get into talking about the x-axis and the y-axis. And as long as you're consistent on your drawings, I'm not really picky. So this gets us to what our displacement is. Our displacement is the change in position. I strongly encourage you to get used to writing in subscripts because that's going to help you along the way. It keeps track of things along the way a lot. You know, this could be the displacement of a car. So I may say the change in X sub C for my displacement of the car. Or I may say I change in X sub T for a displacement of the truck. Or H for a horse or whatever. It's keeping things that are labeled. So displacement, when we talk about displacement, that's our final position minus our initial position. And X and Y variables in kinematics, so if I'm going up or if I'm going in the X direction, those are independent variables. So my change in displacement that's a height will be my Y final minus my Y initial. And I don't care if you use I for initial or 0 as your subscript. That doesn't really bother me either way. So we can look at displacements in cars. There's a displacement. So what's the displacement of that particular car? 14 kilometers. And so I get my total displacement for my car. So I have that displacement, and we've got that spot. So we look at displacement with respect to time. So at t is equal to 0, the car is sitting at 1 kilometer, and then I've got the car at 120 seconds, the car is sitting at 6 kilometers. So I have that displacement with respect to time. And if I do that, there's a 240, and then there I've got it. I went 15 kilometers in 360 seconds, and I can have a position versus time graph. So now we're going to start graphing the data. I've got a position versus time graph. Well, what can you tell me about that graph so far? Got a constant velocity, but the key there is I have a velocity or I have a speed. We don't know yet. In this case, it's kind of both. But the slope of that line is going to tell me, in this case, it's going to tell me velocity. But if that were a curve, the slope at that point would be an instantaneous speed. The difference between velocity and speed is velocity is a vector quantity. When I have a vector quantity, I have direction and magnitude. This is one dimension, so it's kind of a little different, but I have direction and magnitude. So my velocity in the x direction is going to be related back to time, and I'm going to have that piece. Velocity is a derived unit. It's in meters per second. The vector quantity, it has direction and magnitude. It's got speed does not have direction associated with it. It's just a magnitude. It's like going to Tulsa. What was my average velocity versus my average speed in Tulsa? One is I got to worry about the displacement and the time. One, I've got to worry about my total distance traveled divided by time. So I'm going to have a little bit of difference. So I've got vector quantities have magnitude and direction. If you haven't looked at vector addition in a while, remember I can move my vectors around. I can add them head to tail. Okay? I can add them head to tail. The scale, and we talk about magnitude. Magnitude, which does not have a vector associated, magnitude is just a number. That's a scalar quantity. So we're going to talk about scalars versus vector quantities. And that's going to affect our mathematics down the road. We're going to have scalars versus vector. My magnitude of that vector is a scalar. Because I can use a scalar value. So displacement is a change in position. Displacement is not the same as distance. And that's where we were just talking about that if I move 3 feet forward and then backwards 3 feet, my displacement's 0, but the total distance traveled was 6. I'm going to get the same thing if I throw the ball straight up in the air and come back down. I've got a difference. The distance that the ball traveled is twice the height that it went, but the displacement at the end is 0. We get that 0 spot. So the graph, this graph tells us the car's moving. It just doesn't tell us what direction the car's moving. It could be moving northeast. It could be moving straight north. It could be moving, it just doesn't tell us that. So I can do the slope of S in this case is also going to be the speed because it doesn't give me a direction. So I get my change in distance divided by my change in time, and that's going to be my speed. That's why I say for right now, we're going to be very precise about our language. As we go further in the semester, I'll say the speed of the electron is da-da-da-da-da. And I really intend it to be the velocity of the electron. It's a vector quantity. So we're going to get we use these words interchangeably a lot of the time, but you do want to understand that displacement is different than the total distance traveled. And we get our speed. And we can do the numbers. So an average speed, this happens to be an average speed. I can do instantaneous speeds as well. And instantaneous speeds come back and give me, instantaneous speeds are going to come back and give me more the limits as we get to a smaller and smaller finite limit. So I will get that spot. And then I can also look at the average speed if I know the position, okay, or my change in distance. I can do it this way, using my endpoints to convert back and forth between my radial coordinates. But the path length, the path traveled, is not going to necessarily be the displacement. Okay? Not necessarily going to be the displacement. And I think that's where I'm going to stop today.
So what is the change in S? What is the S?
S is the distance. Yeah, S is the distance. We'll use S to mean the path length or the path traveled. Huh? I've used it in the past, but not for this class.